Good morning, TEDxUofM. My name is Elias Schewel, and before I begin, I want to thank Rob Goodwin and Vivian Stockman for helping me put together this presentation. We're going to go today to the mountains of West Virginia, and we're going to look at a situation actually where technology is being used to do very bad things. And we're going to get to West Virginia the same way I got there about a year ago, which is through an interest in hydrology and a little bit of mapping. So first, let's talk about water. So water is always moving. It's either moving downhill, or it's falling from the sky, or it's evaporating and rejoining the atmosphere. So what you're seeing behind me, this is a simple graphic of a watershed, which is one of the basic units of hydrologic analysis. In a watershed, the boundary is formed by an area of high ground. In the graphic behind me, you can see that's a series of ridges. In a watershed, all water that falls is eventually headed into the same river, creek, or stream, or lake. So in a forested watershed, when water does fall, much of it is never going to hit the ground. Instead, it's going to be captured on the complex and dense surfaces of the tree canopy. And in an unforested watershed, or in a forested watershed, when water does fall, some of it will hit the ground. And when it hits the ground, it's going to enter waterways through two avenues. Either it's going to infiltrate through the soil, and it's going to drain through the soil and drain into waterways that way. Or water that can't infiltrate the soil is going to become runoff. It's going to move overland and join waterways that way. So soil composition is also an important part of hydrologic modeling. But vegetation is a big part of healthy soil cover, because vegetation is what allows soil to maintain the properties that make it able to easily infiltrate water. So soil is important to hydrologic modeling and hydrology, but vegetation is what ties it together. Vegetation allows water to be kept and retained on the leaf surfaces, or it allows it to infiltrate better when it does hit the ground. And when you have too much runoff, this runoff moves towards waterways, and if waterways are full, this runoff then becomes flooding. So I'm now going to use a simple physical model here to illustrate the basics of hydrology we've just gone over. So I want you to pretend here that this half of a plastic bottle is a watershed, similar to the graphic I showed you before, and these are the ridges that make up the boundary. And this is, imagine there's a valley floor with a river flowing here. And we're going to pretend that this branch here is vegetative cover. So this is a healthy forest cover for this watershed. And we're going to run two scenarios in this model. I want you to assume in our model that a spray of this bottle is equal to 2 hours of heavy rain and a summer thunderstorm, okay? So I want you guys to count. We're going to set up our watershed model here with our vegetative cover over the watershed, all right? And I want you guys to count either in your head or count out loud how many hours, each of these is 2 hours, how many hours of heavy rain does it take to create flooding at the mouth of the watershed in our first scenario, okay? So count with me here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so at about 22 hours, we start to have water dripping out of the lip of the bottle. This is, in our model, this is catastrophic flooding happening in the watershed, okay? So this is a very simple model, of course. Thank you. Thank you. Just wait. That's just the beginning of the talk. So this is a very simple model here, but what it's meant to illustrate, and I've used it before with different groups of people, it's meant to illustrate that our water resources, good or bad, are an output of precipitation systems, ecological systems like land cover and soil, and topography as well. And so I'm a planner. I'm here in the School of Urban Planning, and I use mapping and geographic information systems, or GIS, to talk about how land cover changes and changes in our ecosystem affect human life and human environments. So with this knowledge, a little bit of hydrology and a knowledge of mapping, about a year ago I went down to West Virginia to do GIS mapping work for an anti-coal group in southern West Virginia called Coal River Mountain Watch. And I went down there. I didn't know a lot about coal, but I knew the basics. So I knew that coal is the #1 power source across the world. Okay? I knew that we here in the United States, we get approximately 50% of our energy from burning coal. And that's dipping down now, but that's because we're burning more natural gas instead. I also knew that 1/4 of the world's coal resources, all of the world's coal resources, 1/4 of them are here in our boundaries. So this is a map that shows coal reserves here in the United States. And you can see we have some in Michigan. It's very cheap, low-quality coal. But we certainly burn a lot of coal here in Michigan as well. So I also went down there. I knew that since the 1980s, strip mining, which is the primary way that we get coal here in the United States, strip mining activity had accelerated greatly since the 1980s. With application of new technologies and then deregulation that allows those technologies to be brought into the field and used. So what you're seeing here in this diagram, in the top image is the before. In the black seams there are coal running through a ridge line there, or through a mountain. And in the bottom we see how the coal is extracted. So it's dug out and the mountain is essentially removed over. The whole thing is dug out and slowly moved over to get the coal out. So this is what that looks like in real life. So as you can see, it's a serious feat of engineering. Major technology is being applied here to make this happen. So this is what this looks like in real life. So this image here, all those red blobs you're seeing here, each of them is permitted strip mine activity in the state of West Virginia. So this is something the West Virginia Department of Environmental Protection has said is okay to mine. As you can see, it's quite extensive. This activity, strip mine activity in West Virginia alone, affects tens of thousands of families. They're digging out coal for us to burn in our power plants. So of all the different ways that coal extraction kills people through poisoning their water, depleting their water supplies through fractured aquifers, poison coal dust that enters people's homes and their lungs. As you can tell, my work is largely focused on land cover change and mapping. And so this is one of my study areas. This is the Laurel Creek watershed. It's in southern West Virginia. And what you're seeing in this graphic is the light maroon color is strip mine activity in 1996. So in 1996, that's where they were at in this watershed. Then the dark red is what they mined from 1996 to 2003. And then the orange is what they mined from 2003 to 2009. But let's zoom out a little bit. Let's combine this map. And so in my analysis through this, in this study site, strip mining increased 320% from 1996 to 2009. But let's combine that map with the map I showed before of all permitted activity right now, what they could mine. If they had all the equipment and all the employees in the world, what they could mine right now. So we zoom out a little bit, we can see the lighter orange then is what those red blobs were in the earlier graphic. This is all currently permitted strip mine activity. And so if we zoom out again, we can see one of my study areas in its environment here in the rest of southern West Virginia. So if nothing changes in our energy policy and our energy consumption, all of this could be gone in 20, 30 years. So this table shows research being done by a woman named Jen Osha at West Virginia University. And she is doing surveys with people in coal extraction areas to outside of the technical discourse, outside of the permitting process, outside of the legal dialogue, to survey people and understand how they see coal extraction impacting their communities, their families, their landscape. So as you can see, increased flooding is, most respondents, 90% of respondents have listed increased flooding as their #1 perceived impact of strip mining on the landscape. So they're able to see it in their communities. I spent time down there last summer. Flooding is something that happens all the time to people. The hydrology of the area is constantly changing. Houses are constantly getting flooded out in their little hollers or down in the towns as strip mine activity expands on a site. And so this is common sense to people living down there. It should make sense to you guys after the basics in hydrology that you've gotten now. But the permitting allows it. It's perfectly legal, and it happens as you saw in those maps. You saw exactly how much area is permitted to be strip mined in different watersheds across West Virginia. So this flooding kills people. I showed a picture earlier of a house being flooded. It destroys property. And it also kills people sometimes. People will be drowned by this flooding. And so we're going to go right now, and we're going to look at a permit. In 1998, flooding in a town called White Creek killed 2 people. And I'm not able to reconstruct the hydrology of that area, figure out which mine in the mine complex contributed the most runoff to the flooding that would eventually drown 2 people. So instead, I dug up a mine permit for a mine from the same area. This is from adjacent to this mine complex that drowned these 2 people. It's from 1996. That that flooding that drowned those 2 people was in 1998. And there have been other drownings since then, certainly. This is just one that I could find a reasonable permit to compare. This is from the same era. It's from adjacent. And this is for the Skidder Creek #1 mine. And we're going to look at the portion of the mine permit that deals specifically with hydrologic concerns. So where they're supposed to write up whether this is a good idea based on what it's going to do to the hydrology of the surrounding area. It's going to cause flooding, things like that. So this is called the Cumulative Hydrologic Impact Assessment, or CHIA. I'm going to refer to it as the CHIA. And we're going to go through it. But don't worry, this isn't going to get too boring, because even though this mine would eventually disturb 600 acres and it'd be active for 8 years, pulling out hundreds of thousands of tons of coal, despite all that, the permit dealing with the hydrologic concerns is only 3 pages long. So this won't take too long to go through it. So this is the introduction page, and we're going to spend a little bit of time here, because what's important here is right at the top, they tell us, and I unfortunately didn't highlight this in the slide, but it's at the bottom there, they tell us that everything else that you're going to read in this narrative assessment is all based on analysis put together by the coal company, based on data created by the coal company, and that there's not going to be any independent analysis done of the conditions on the site beforehand or on the conditions of the site afterwards to model the hydrology there, outside of what the coal company tells them the hydrology is like. So this is the second page. This is this portion called the hydrologic concerns, and in it, up top, the guy details, the inspector, the guy or gal, details that a mine of this size, 600 acres, is going to be clear cut, topsoil is going to be scraped off, they're going to blast it apart, and he says there may be flooding concerns from that, but he also tells us later on that the company is going to use sediment control procedures, and we'll see what that looks like, and they're going to use reclamation, which means they're going to set the site back to its original hydrologic conditions as they move across the site. So 8 years, 600 acres, they're going to tear it up and move down the ridge line. But as they move, they're going to replant behind them to make sure that the vegetative cover, therefore the hydrologic profile of the area, is the same as what it was beforehand. In a second, we're going to see what all of this looks like, but I want to show you guys in words, written up by a technical analyst, what this process looks like on paper. So the final page is their conclusions. And in it, he tells us that, or she, I didn't look up the name of the person who did this, they said, based on the available data, there's nothing to worry about. So technical analysts put together something at the coal company, and a technical analyst here, in this case the West Virginia DEP, reviewed it, and there's no reason to be worried about anything. Despite whatever common sense you might be looking at this with, you have nothing to worry about if you live in this area. So now let's look, this again, not the same mine site that drowned those 2 people, and this is not the same mine site that's contained in this application, but it's a mine site very nearby, basically on the next mountain over. And luckily, through the help of some activists down there, I have photographs of this mine site from before, during, and after mining. So you can see everything they're talking about in this permit, how they're going to return it to its original hydrologic profile. So this is what a site like this looks like originally. Rich, ancient forest, okay? The glaciers never came down far this south into southern Appalachia. So you have 100,000 years of topsoil, amazingly rich ecosystem. This is what it looks like on the ground. As you can imagine, all that vegetative cover, very good for blocking precipitation from hitting the ground, very good at making sure that precipitation does infiltrate. Okay, then they're going to change the site. Oh, this is what it looks like from the sky as well. This is a beautiful aerial shot in the fall of a mine called Sugar Tree Mine before it was mined. So this is what they're going to do first, is they're going to clear cut it to make way for the blasting. All right, and this is a picture of it from a different side. And you can see behind me, that pond there is one of these sediment control structures that they noted is going to prevent flooding on a 600-acre site. Now you'll notice in this photograph, the sediment control structure is already filled with water, which makes you wonder that if it rains today, what that's really going to do to actually stop flooding, right? It can't hold more water, it's already full, so it's not going to be of much consequence. And this is what the site is going to look like for 8 years. Okay, it's going to be an open strip mine. They're going to be blasting apart the mountain, moving the rock, which is called the overburden, to get at the seams of coal. So this is what that looks like. And then they also told us in the permit not to worry about flooding, even though the site is going to be active for 8 years, 600 acres. Don't worry about flooding, because they're going to reclaim as they work along the site, right? So let's see a picture of what reclamation looks like. Okay, so this is what reclamation looks like. As you can see, very different hydrologic profile. Yes, there is grass. That grass is hardly growing in soil. Let's look at another picture. It's almost an impervious site with a light layer of grass. So imagine what you saw happen to the bottle when we turned a vegetative surface into an impervious surface, right? Now imagine that, what happened in that small area playing out over 600 acres, okay? And then go back to the maps I showed you of what southern West Virginia looks like, where there's permitted strip mine activity. And imagine what's happening in that bottle playing out now over an entire state. And then realize that those mine permit boundaries don't stop at the boundaries of West Virginia. At the state border, they go out into Kentucky and to Virginia. And then remember, think about what's happening in that bottle and think about happening over a region, an entire region. Okay, whole parts of Appalachia are being strip mined right now. So I have no doubt that maybe somebody here in the audience today is going to invent a technology that will allow us to burn coal without emitting CO2 or mercury. So if we're really concerned about global warming or poisoning the oceans, maybe we can continue to burn coal the way we do now. But that's not going to do anything for the people that are affected by the extraction process itself. And so what I see here in these pictures and in the process I've described is I see an incredible power for technology and engineering to meet our energy needs by tearing apart a mountain, destroying the ecology, and beginning to poison the local community. And I see technology and engineering, again, being used in a model to figure out the best way to do this. But that model is only as good as the assumptions that are put into it by its operator. And so the real problem here is politics, right? The way the legislation was written years ago, no one does any independent analysis or independent review. And so what I see here is I see a technology that I love, which is mapping and modeling. This technology is not being used to analyze the consequences of a land use decision or land use change. This technology and engineering is being used to mask the consequences of our national energy policy, which is that people have to die. So I wonder what engineering and technology can do to help us solve the really big problems and the really big questions if it's asking the wrong questions as an area of study, asking the wrong questions to get there, which is that we can't keep doing things the way we do them now, but faster or cheaper or more efficiently. Because for me, faster hydrologic modeling is not going to help communities impacted by flooding if the political system can't come up with a viable alternative. And so we need coal now, and we're going to need natural gas just the same, because we don't care how we get it. And so in this case, what I see is I see a normative decision that already happened, and then the technical analysis being used to cover up the process for making that normative decision. So we like to think that our normative decisions are being driven by rational values-free analysis, but in fact, this is the exact opposite. A normative decision has been made, and rational values-free analysis in the form of this runoff studies and these permits is being used to cover up the normative decision or to justify it. And so before I go, I want to say I'm so honored to get asked to give a TED Talk today. And I feel very lucky to be getting the education I am here at the University of Michigan. For all the students and grads, I hope you also feel lucky. And I hope that you will think about ways to use the privileged knowledge that you've gained here to not graduate or wait to play your part in a broken system, but instead to find a way to change that system. And so particularly to people with technical skills, engineers, technicians, technical analysts, mappers, programmers, my ask is that you find a way to hack the system and change it instead of waiting to play your part in a broken system. Thank you.